Hello students, welcome to the fifth session of our first module. And in this session, we are going to discuss about aircraft refrigeration or aircraft cooling systems. Okay, aircraft cooling systems. So in aircraft refrigeration, the advent of the high-speed passenger aircraft, jet aircraft, and missiles has introduced the need for some compact or lightweight or simple kind of refrigeration system, right? Why? In order to decrease the weight or the bulkiness of the system, refrigeration system should be avoided. So we require some simple kind or need compact, simple kind of refrigeration systems are required. So aircraft refrigeration systems are employed for air conditioning, cockpit and cabin of the cabin of the aircraft, right? So this is why we require aircraft refrigeration. So students, we know plenty of air is available outside the aircraft while it is flying, right? So since the aircraft is flying at very high altitudes, the temperature will be low at high altitudes. Temperature will be low, right? Temperature is low, right? So we have some cold air available outside the aircraft, but still we require cooling of cabin. Why? Because large internal heat generation will be there due to occupants and equipments also, right? So we have occupants, equipments, all generates heat. So we have to throw this heat away, or we have to remove this heat. Also due to some skin friction, heat generation due to skin friction at the surface of solid and fluid in relative motion. So since the aircraft is moving with high speed in air, there will be a friction at the surface of the aircraft, friction between that solid surface and fluid in relative motion. Such friction is called skin friction. Skin friction will generate heat. Okay, so these heats should be removed. So that is why we require aircraft cooling system. So at high altitudes, the outside pressure will be less than atmospheric, right? So when air at low pressure is compressed, what will happen? And since the pressure is very low outside the aircraft, this low pressure is to be compressed and supplied to the cabin at atmospheric pressure, right? Okay, I'll show. If this is my aircraft, okay. So here outside aircraft pressure will be less than 1 atm, right? Atmospheric pressure, less than atmospheric pressure. We have to pump this air into the aircraft system, right? So while we are pumping, we are supplying this air to aircraft inside the aircraft. The pressure should be increased to 1 atm, because people are sitting there. So pressure should be around atmospheric pressure only. Okay, that will be the comfort. That will make comfort to the occupants, right? So it should be compressed and supplied to the cabin at pressure close to atmospheric. While compressing, if we compress the air, what will happen to temperature? If P increase, means temperature will also increase, right? So even though the outside temperature was a little bit low, So while we supply, we are compressing it. So while compressing, automatically the temperature of the supplied air will also increase, right? So for example, if outside pressure is some point 0.2 bar and temperature equal to some 223 Kelvin, around some 223 Kelvin, means it is negative, right? Negative in Celsius at very high altitude. While we are supplying it, it will be compressed P equal to 1 bar or 1 atm, around 1 atm. Temperature will become, actually if it is compressed from 0.2 to 1 bar, its temperature will naturally will become some around 350 Kelvin. 350 Kelvin means some 77, around 80 degrees Celsius. So this much temperature cannot be afforded by the occupants, right? So if the cabin is to be maintained at some around 1 bar, the temperature should be about some how much, 300 Kelvin, right? The students, if our aircraft is at some height such that the pressure is outside pressure is some 0.2 bar, temperature equal to some minus degree Celsius, some 223 Kelvin. So we have to supply this air. Suppose if we are supplying to some in P inside, this is P out, okay, T out. So P in is some 0.8 bar or around 1 bar. Naturally, T in should be around some 332 Kelvin around. If P in equal to 1 bar, T in will be around some 350 Kelvin. So this effect, okay, so this effect of increase in temperature while we are supplying the outside air, ambient air into the cabin or into the aircraft is called ram effect. This is called ram effect. Ramming. What is this? This effect, the effect of increase in temperature while we are supplying the outside air by compressing it into some atmospheric pressure. So that increase in temperature is called ram effect. This effect adds heat to the cabin, right? Since this has got higher temperature, it means we are adding heat to the cabin, so which needs to be taken out by the cooling system, okay, cooling system. So there are we have discussed many uh, factors for the reasons for applying cooling system. What was first one? Occupants, okay, occupants, equipments, skin friction, ram effect. So all these things make us or wants us to apply cooling system. And fourth one, solar radiation. So all this will cause increase in temperature inside cabin. So in order to counter the effect of increase in radiation, what will we do? We will apply cooling system. Okay, we will apply cooling system. So simple. Now we will discuss various types of air cooling system. Okay. So why we are using air as the fluid? Why? Why? Why we are using air as working fluid? Air is non-flammable, right? Non-flammable, non-flammable, non-toxic, non-toxic. Okay, air is free. It is available plenty outside the aircraft, environment friendly, and maybe one important factor is air refrigeration system per ton. Air refrigeration weight of air refrigeration system per ton of refrigeration. TR means tonnage of ton of refrigeration. This is a unit. Is low. So since weight is low, it is very useful in case of aircraft. So for all these reasons, we use air itself as the working fluid, right? And there are other reasons also, maybe uh, the leakage of air is not a problem. Even if there is leakage of air is not problem, right? uh, then the cold air can directly be used for cooling, thus eliminating the low temperature heat exchangers, and we will understand that it is non-corrosive. All these things, there are numerous factors. You just read those factors from your textbook and try to understand different aspects of air being the ideal working fluid in case of aircraft operation. Okay. Now we will move to different systems. I will explain first one, simple air cooling system. So I will draw the diagram. So students, this is a simple air cooling system. So this is our aircraft system. Okay. We have got air, atmospheric air from here, ambient air. Okay, this is ambient air. When it enters aircraft, what happens? Ramming takes place. So this is ambient. Okay, ambient air when in this aircraft cooling system, ram effect takes place. So this is my compressor. This is a gas turbine. Okay. So this rammed the air that has undergone ram effect will get compressed and will move downwards. So some compressed air will move this way, some will move this way. So this compressed air will undergo some combustion chamber. Combustion chamber. So this will be fed to the gas turbine. So the gas turbine rotates, and this gas turbine will give power, will power the compressor. So this cycle happens here. So this is how compressor works. Compressor get power from gas turbine. Okay. So some of the compressed air will move to a heat exchanger. So this rammed effect, the air which has entered the aircraft repair system will have a higher temperature and higher pressure. Okay. So this higher pressure, higher temperature is again pressurized or again compressed to a even higher pressure and even higher temperature. So this hot temperature is passed through a cooling chamber or heat exchanger. So this rammed effect, some ram effect, so this some of this air will get bypassed through this, and since the temperature of this compressed air is higher than temperature of this air. Okay, I'll show you. So this air will be somewhat cooler, right? Somewhat cooler than this red colored air, so because it is compressed air. So this cooler air will absorb heat from here, right? Absorb heat from here. So this heat, this air will be cooled and even cooled again when it is passed through some cooling turbine. Cooling turbine. Okay, cooling turbine. This is cooling turbine. Okay, when it is passed through cooling turbine, its temperature will again get reduced, and this cooled air will be moving to cabin. So this is cabin. This is the direction to cabin. Okay, so how this cooling turbine works? Cooling turbine works why this rammed air will pass through this fan, and this fan rotates. This will give power to cooling turbine. The rotation of this fan will give power to cooling turbine. So this is how simple aircraft refrigeration works. Okay, so students, this is a picture, a better picture showing simple what simple air cooling system. So the ambient air comes and it is rammed here. Some of the rammed air bypasses through this way and it moves through this. Okay, since this is compressed air, so this is rammed air, so there will be some heat transfer from this air to this air. Okay, so this air will get cooled and it will again get cooled by what? By cooling turbine. So how this cooling turbine works? So this air will rotate this fan. This fan will allow the cooling turbine to rotate, and this cold air will enter air cabin. So that's how things work here. Okay, now students, can you draw this process in a TS diagram? Temperature entropy diagram. How can you draw these process in a TS diagram? Temperature entropy diagram. Suppose my ambient pressure, you know that this is how a constant pressure line looks like in a TS diagram. Suppose this is my ambient pressure, or the pressure outside the aircraft, ambient pressure. Suppose this is the inlet, the position 1. Okay, I will show you. Here. So this is what? Position 1, state 1. Okay, state 1. So here state 1. From state 1, what will happen? It get rammed at constant entropy, adiabatic process, rammed to a higher pressure. So this pressure is known as ideal ram pressure. Ideal ram pressure. Okay. Now, ideal ram pressure is not always possible, and this is assumed as a isentropic process, but isentropic process is not actually possible. So most probably it will be somewhat like this, but at same temperature. So this temperature will be same. So this will be this was supposed to be 2, this was supposed to be 2 dash. So this pressure will be actual ram pressure. Okay, so P2 dash is actual ram pressure. So now it is at 2 dash. So I will show this in my my diagram here. So here it will be 2 dash. Oh, so from 1 to 2, 2 dash. After this, what will happen? Compressor, it will undergo compression. 2 dash to some 3 dash. Okay, so ideal will be 3, actual will be 3 dash. I will show you. From 2 dash, what will happen? It get compressed to some main higher pressure, or main compressor pressure, or compressor pressure. So this will be 3. Okay, so isentropic process is not actually possible, because isentropic process is a reversible process. Such process are not possible. So naturally, what will be the pressure? It will be some 3 dash. Okay, 3 dash, but the pressure will be same, P3. The same, it will be in the same pressure line, but temperature will be high. So this is T3 and this is T3 dash. Okay, so from T3 dash, what will happen? From T3 dash, I will show you. From T3 dash, it undergoes what after it will lose some heat to some 4, right? Constant pressure, since it is undergoing a cooling in heat exchanger. So this is heat exchanger. It will undergo constant pressure cooling to state 4, right? To state 4. So what will happen? So along this same constant pressure, from 3 dash to some 4, so this temperature will be T4. So along same constant pressure line, the temperature will get reduced to some 4. And after 4, what will happen? It undergoes what? After 4, it undergoes some cooling turbine. It will undergo cooling through cooling turbine. So it will be some, so 5 dash. Constant entropy or isentropic expansion takes place in turbine. What will happen? Expansion takes place. Okay, I will show you the expansion. Since it will get expanded to some this temperature. What is this temperature? This is 5 T5. Okay, what will be this pressure? The pressure of this pressure will be somewhat this is PC, cabin pressure. Okay, since this air enters cabin, the pressure should be equal to the pressure that is maintained in cabin. So this is actual process, but so this is ideal process, but actual process is 5 dash, because it won't be reversible or isentropic. Okay, so this is 5 dash, and from 5 dash, it will get heated in cabin. Refrigeration takes place in cabin to some 6 or any other point. So our process is 1 to 2 dash, 2 dash to 3 dash, 3 dash to 4, 4 to 5 dash to 6. So this is our process. But this process is not cyclic, because starting point is 1, ending point is 6. Why? Because air is not recycled. The air is taken from the atmosphere and used to cool the cabin, and the cooled air will be again thrown out to atmosphere. But not the same air is taken. So this is an open system, not a closed system. That is why this has not become a cycle, right? So this is the process of what This is the TS diagram for our simple aircraft refrigeration system. So two more aircraft refrigeration system is required to study, and I think problems based on this cycle are used to be asked in to university exams. So if you understand this cycle, probably you will be it will be easier for you to solve those problems. Okay, so for the time being I am stopping this session, and in the next session we can complete the other two remaining systems. Okay.